right, guys, so today we are starting chapter 6. This is going to be the last chapter we're going to cover. Now, most likely, because again, there will be a schedule for finals. This chapter test is going to be your final test. And just because of how the days fell and how everything's falling, most likely the final for this class is not going to fall on the math days final. Because to fit everything in and to get the makeup days and all that in, we're just not going to have time. Does that make sense?
We got 4 weeks, right?
Yes. So the test, I think y'all's final for math is supposed to be like 2 or 3 days before we're actually going to be able to do it. It's just going to be scrunching everything in. And what we're talking about in this last chapter that we're going to cover is exponential and logarithmic functions. Exponential functions and logarithmic functions. Now, an exponential function we're going to look at is b to the x, where b is greater than 1. It's going to be any number. So we could say 2 to the x is an exponential function, where we're inputting the values of x, our domain, into the exponent. And they say this is exponential because the values for this function are going to increase at a faster and faster rate. So if we looked at, say, 2 to the x, so y equals 2 to the x, and said graph. Well, we can see here it increases faster. Now, if we look at the table, well, okay, it's going to be easier to use the arrows than it is to try to type this on the getting closer. Almost there. All right. Now, when we look at the x value, so for when x is 1, so 2 to the first is just going to give us 2. 2 to the second would be 4. 2 cubed is 8. 16, 32, 64, 128, 256. So in the first, so 256, the other direction now, is 8. We get to 10, 2 to the 10th, we're at 1024. The amount of gap between one and the next is increasing faster and faster. So 11, we're at 2048. By the time we hit 19, we're at 524,288. By the time we hit 20, we're at 1 million. That's increasing at quite the fast rate. That's why they call these exponential functions, because the amount of growth from one to the next is increasing at a faster and faster rate. And that's just with 2. So if we said 9, and looked at its table, well, for 9, by the time we hit 9 to the 6th, we're already at 500,000. So we didn't even get to 10, 9 to the 10th, before we broke 1 million. So these functions can increase faster and faster depending on their growth. Now, we consider a function to be an exponential growth function where the value of b is greater than 1. We don't include 1 because, well, 1 times itself, no matter how many times we do it, is still what? 1. It's not growing. So whenever this value of b is greater than 1, it's going to be considered an exponential growth. Now, we don't consider negatives because they behave a little bit weird, and especially when we start dealing with powers and roots, they'll start behaving differently. And an example of that would be saying -2 to the x. Second table, because this is not a function. That's why I didn't graph it. Because if we look at the third, 2 to the third is -8. 2 to the fourth is 16. So it's oscillating between positive and negative. So it's not really a function. So we don't really consider when b is negative. We just want to focus on the positive cases. So any questions on this so far? So if b is greater than 1, it's exponential growth. Now, as I just said, we don't talk about negatives, so the only other setup that we can have is if b is between 0 and 1. So a half. So we can say 1/2 to the x. And this would be considered exponential decay. So the function is going to be decreasing. So we can say y here instead of, we can say 0.5 because that's 1/2. And if we graph it, it's decreasing. The values are getting bigger in the denominator. Now, with this here, do we think this will ever actually get to be 0? Well, no. Let's look at the function itself, because 1/2 are exponential properties. We're saying that we can apply the x to the numerator and the denominator. Well, 1 to the x, no matter how many times I multiply 1 by itself, it's still going to be 1. So really what we're looking at here is 1/2 to the x, yes? On the previous one, we saw 2 to the x is going to get exponentially big. It's going to keep getting bigger and bigger, yes? So the denominator, the bottom of this fraction, is going to get exponentially large. What's the only way we can make a fraction be 0? Multiply by 0, or what number is in this fraction would make it 0? Or what part? The top or bottom? The top, right? Because 0 over anything is 0. So the only way that this can be 0 is if the numerator is 0. Well, what's changing? Just the denominator. It's getting smaller, but it will never reach 0. This is our normal function, this here. Are there ways that we can make it 0? Well, yes. I could just take this, erase. -1, because I've just taken all the points and moved them down 1. But now they can't reach -1, because I just lowered all the points. But for our normal function, f of x equals b to the x, this can never equal 0. It can never be 0. The same is true for this one here. For our normal function, it's not going to get to 0. The value of y, essentially, we can't plug in any value of x and get 0, no matter how this works. For our normal function, the only way we can do it is if I start moving the function up or down. So this here is considered exponential decay. Questions on this here? You ready for something challenging? Let's go this way. Y equals 2 to the x. Is this exponential growth or exponential decay? Y equals 1/2 to the x. (1.3 to the x). Growth, because it's greater than 1. Even though it has a decimal, it's still greater than 1/3. Because it is less than 1. (4 to the x). Y equals 2/3 to the x. Because 2/3 is less than 1. 0.25 to the x is decay, because that is less than 1. F of x equals 1.5 to the x is growth. It is greater than 1. Questions on this here? Exponential models. So these here you've probably seen in your PFL class if you've taken or taking PFL. Because we can define growth and decay as a times 1 plus r to the t. where r is our rate and t is time. For exponential growth, exponential decay, we're saying a times 1 minus r to the t. Or again, r minus, or 1 minus r is our rate of decay. So, the value of a car, y, in thousands of dollars can be approximated by the model y equals 25 times 0.85 to the t, where t is the number of years since the car was new. A, tell whether the model represents exponential growth or exponential decay. What do y'all think? So what's growth going to do? It's going to get bigger, yes? Decay is going to get. So if we had not covered any of this here, I'm talking about what? Value of a car, yes? Does the value of a car go up once it's been released? No. So knowing nothing about this lesson, what is it going to be? Okay. Also, our model, well, it's going the wrong way. So exponential growth is equal to a times 1 plus r to the t. Exponential decay is a times 1 minus r. So r is our rate of it either growing or decay, yes? So as we said with a growth, the rate or amount that we're growing should be greater than 1, yes? And if it's decay, it is between 0 and 1. So what are we having here? 0.85 to the t, our variable. 0.85, is it greater than 1 or between 0 and 1? So this here would be a decay. Identify the percent increase or decrease, and it's not 0.85. Because our model for this here is a times 1 minus r to the t. Well, where's our rate? It's in here, yes? 1 minus r. So for our rate, 1 minus r is what? It's 0.85. So if I want to find the rate, what can we do? Well, I can subtract 1 from both sides, which tells me that negative r is equal to negative 0 point, or our rate is what? 0.15 or 15%. So it's decreasing 15%, I think, each year. Yep. So it's decreasing 15% in value each year. Not terrible. Not great, but I mean, that's about on par. Questions on this here? Well, that brings us to the last part. Okay. There we go. Nope. Any questions on any of this here? So the percent decrease is 15%. Now the last part is figure out how many years is it going to take it to be $8,000? Yes? They already gave us the equation, didn't they? 25 times 0.85 to the t. I can go y equals what was the first number? 25. 25 times 0.85 to the, for this here, are we going to use t? No, we can just use x, and we can graph it. And it doesn't show up. Well, let's put it in a standard negative 10 to 10, negative 10 to 10. We get this graph, yes? Well, it's kind of hard to see, so let's look at the graph, or the table. Well, all these numbers are really small, aren't they? because we're trying to see when it's 8,000. Well, none of these are 8,000, are they? Let's look back at what this says. The value of the car, a car, y, and what? Thousands of dollars can be approximated by this model. So the 25 is not 25, it's what? 25,000. So I'm not looking for 8,000, I'm looking for 8 because it's defined in thousands. So when I look at this table, when x is 3, that's not 15.353, it's 15,353. Now this seems a little odd to do this, but what this does is it makes it easier to graph. Because instead of looking at 15 and moving by thousands, we're now moving by ones. A little bit easier to look at. So when does this graph hit 8? 7. So after how many years? After 7 years, it'll get to approximately 8,000. Now, is that the exact amount of time that's passed? No. Do we have a way to find that yet? Not yet. Are there ways to find it? Yes. Have we gone over ways to find it? Well, no. That's what this chapter is, and that's what we're going to be getting to, is being able to evaluate these functions. Because up to this point, we don't have any way to get a variable out of an exponent. We just don't have it. You've seen some ways to cover this. One of them is 1-to-1. 2 to the x is equal to 2 to the 4th. X equals 4. You've covered those, and we'll cover those again. But what we'll dig into is when we don't have nice numbers. Any other questions on this here? This is the last thing we'll look at compound interest. This is kind of nice to know and how it works, but at this point it's kind of become not as important because there's lots of different things that'll do this for us. There's even calculators that'll calculate everything into it. You can actually put the percent interest, how many times it's compounded, and what you're paying into it, and to see what the actual payments or what interest would be after so many years. You can also do some that do compound interest for like a savings account where you can actually calculate in what interest you're gaining as well as putting money into it. Now this here, compound interest, P is the principal, the amount that starts out, how much you have to begin with. R is our rate expressed as a decimal. N is the number of times it's compounded per year. And T is the amount of time. And A is what we get out of it. So P is equal to 1 plus R over N to the RT. So this is the last problem we'll actually look at today. You deposit $9,000 into an account that pays 1.46% annual interest. Find the balance after 3 years. Looking at this here, so our amount that we want to find is equal to our principal, which is plus 9,000 times 1 plus, so R over N, our rate is, so 1.46%, but we want to express it as a decimal, which would be 0.0146, because we got to move the decimal 2 places to the left. So N is the number of times it's compounded. Annual. Annual means what? Every year. So it's going to be over what? 1. Annually. Once every year. To the NT, so 1 times. No, sorry. I wanted to grab it from here, but this is not it. When the interest is compounded quarterly if I can finish reading the sentence. Quarterly is every what? 4. Quarter? 4. Sorry about that. Any questions on what we did this, got this here besides the little goof up for the 4? We good with this here? That's what we do now. Solve it. Type it in. 9,000 times 1 plus 0.0146 over 4 to the 4 times 3. $9,402 and 21 cents. That's it. Any questions on this here? And there's other stuff we can do with this here. And one of the other big things with exponential growth and exponential decay that you see it a lot is more exponential decay. And we talk about it as half-life with radioactive elements or radiation. We talk about half-life. That's also why Chernobyl, going and seeing parts of Chernobyl it is possible now, and you can actually tour through Chernobyl. Yeah, but you need to have hazmat suits, lead, whole 9 yards. Because again, one of the nuclear reactors in Chernobyl ended up having a malfunction, so it's leaking radiation. They have a fix for the time being, which is putting a dome over the top of it. But it's still very radioactive, very bad. If I remember correctly, one of the rods got too hot and they couldn't cool it down fast enough, so it ended up having a leakage, and it's pretty much done a number on it. So, but again, by the time the radiation is going to be completely gone, most likely we're going to be completely gone. Because, let's see.